So, functional programmer, right?
Yes.
That means you like to write programs. And of course, you want to write programs that are easy to use, and you never want to do work that somebody else did, right? Okay. Of course, everybody keeps telling me, the world of decision procedures has really gotten smart, okay? There are these decision procedures that are efficient, they solve really big problems, and, they really can help us. But how do I combine an off-the-shelf decision procedure with some problem that I really have, right? So, well, I guess, what do I have to do? I have to learn how to use one of these tools, right? Then I have to build some input to the tool. This is an input to a CLP solver, and that's an input to Yikes, which is an SMT solver, and that's an input to MiniSat, which is a SAT solver, right? How do you come up with these things, right? Okay, I mean, the problem that you want to use one of these solvers on is really some component of some bigger thing that you wrote, right? So that's the problem that I'm thinking about trying to solve here. Okay, so I have some problem that I want to solve, and there's a part of that problem which could be solved by a decision procedure. So what do I have to do? Well, I have to learn some new tool. I've got to read about SAT solvers or SMT solvers. I have to take whatever problem that I have, and I have to encode it in that tool's paradigm as a SAT problem or as an SMT problem, right? And somehow I have to construct an input file. It takes me 2 days just to understand what the format of the input file is. Okay, then I have to run the tool and extract the solution, and then I have to take that extracted solution and somehow get it back into my other program, okay? And so after I've done that, well, what do I've given up, okay? It's too much work. I don't want to use these tools, okay? And then I want to use another solver. I have to do it all over again, okay? So I started to think about, well, what happens, okay, when you embed a solver? What kind of things happen over and over again? Can we abstract over it? How could we embed this in a kind of general purpose programming language? So that's what I've been thinking about for a while. Okay, so first of all, let's go back for a second, right? So we're functional programmers, so we're really declarative programmers. We want to say, what, not how, okay? So in the functional paradigm, what do? We say, well, I have some input, and here's some rules that transform the input to the output, okay? And so, but there's this other declarative thing, this logic thing. It says, well, I want an answer that has this property. It's a list of length 7, and it's the same elements as the input list, all this other property. Okay. So what I really want to do is sort of combine these things, okay? So functions, right, they describe an answer for every input, but a logic program could have many answers, okay? It says, I want some answer which has these properties, and maybe there's more than one, okay? So if you really want to combine logic and functional, it's all about reconciling the two approaches. Okay, one, you kind of describe how you manipulate data. The other, you describe the properties you want data to have. One always gives you a unique answer. The other gives you possibly multiple answers. Okay. So the approach I use is this thing which I call an existential declaration. Okay, so declarations introduce names that stand for values. So I say, so there's a finite set, small, which is a set of integers. I'm going to give some values and some computation goes there. Since it's a set, if there are duplicates or the order doesn't matter. Z is equal to x plus 9, so I compute something, okay. Here's a function. I describe how it operates on data. And then there's this thing here that says there exists an x, okay, which is a list of smalls where p of x and length of x is greater than 3. And what I would like is some x that meets that property. Okay? And so what I'm trying to get here is that there's a kind of modality of computation here. So we're used to working in what I call the evaluation modality. You name something, there's a computation that runs, produces a value, and assigns that value to the name. But then there's also this find, or this existential modality that says, there is an X, and find me one that has some property. Okay? And I claim that this existential declaration is perfect for embedding decision procedures. So here's my first example. So this is, I have a bunch of factories and a bunch of stores, and I have some costs for shipping things, and I have some expected sales in the stores, and so I want to figure out how many objects I should manufacture in each factory so that I produce enough things for each store, but since it costs to ship these things and the cost for shipping is different in each factory for each store, I want to sort of maximize and minimize my data here. So I say, well, so here's some pairs, that's the finite set of the cross product of factory and stores. Okay, so I think there are 6 of these or 9 of these things. Sales, so it says I expect 230 in store A and 140 in store B and 300 in store C. And they said, then there's some production thing. And it's an array of pairs of factory and store and an integer. It says, so factory A sends to New York City 52 widgets. Right? And there exists something like that. Okay? And what do I want? Well, so I have some constraints here. Okay? I say, well, I don't have a pointer. If you say for every store, I take the production at store A and S, and that has to be less than 150. What does that mean? Well, it says that factory A is small and it can't produce more than 150 elements. Okay, and the production for every F and every S is 0. So what does that mean? I produce at least one thing for every store. Right? And the sales have to add up to the things in the factory. I don't want to produce too many and so on. Okay? And then I want to minimize this objective function, which minimizes the shipping cost. Okay, so what did we do there? We declared some data types. We wrote some functions that manipulated those data types. We declared one or more existential variables. We wrote constraints about those variables using the functions. And then somehow that existential variable is attached to some decision procedure, okay, that essentially assigned a value to that existential variable. And then later on in my program, I could use that variable just as if I had computed it. So here's another example. This is an n-queens solver. Okay, so I have some things here. So there's this size. This is a 4-queen solver, but if I change size to 8, I get an 8-queen solver. I have some width, which goes from 1 to size. I have some I2, 0, 1. There's a queen there, or there isn't a queen there. Okay. I have some row points and column points. It says I get a bunch of points that indicate row I or column J, or diagonal I or diagonal J, okay, and so on. Okay, so I have some functions that compute these things. And then what do I say? Well, if I add up all the rows, I get 1. If I add up all the columns, I get 1. If I add up all the down diagonals, I get at least 1. And if I add up all the up diagonals, I get at least 1. So that's sort of, there's at least, that you get a solution. Okay? And then I want to solve that with some solver. Okay? All right, so what are we going to do to embed a solver? So we're going to pick a solver. We're going to have to solve 7 problems. Okay? So the input to the solver represents something. So I have to choose a data structure that represents the input that I'm going to throw at the solver. Okay? And essentially, if you think about it, the constraint is a Boolean valued expression, right? Okay, so the input to the solver is somehow related to the Boolean value that I write, exists x, some p that mentions x. Okay? And so what I want to do is I want to say, well, look, since that's a Boolean function, I want to overload some of the Boolean operations. Okay? And those overloaded operations are going to produce the first representation, the thing that I'm going to throw to the solver. Okay? Well, I have to initialize those existential variables. Okay, I said, you know, go back here. That board, I have to initialize an array of I2s, and up here, I have to initialize a production, which is an array of factory cross stores of integers. Somehow I have to initialize those things. Okay, I have to generate all the constraints. Okay, okay. I have to deal with this problem of lifting and staging, okay? Because some of the functions and data in the constraints work over real things, and some of them work over existential things. So there's really a staging problem here, partial evaluation problem. I have to put that into the format for the solver. I have to run the solver, and then I have to extract the solution. Okay, and put it back in the program. So I've now embedded 4 different solvers, and they all have these steps. So I only have time in today's talk to show you one example of this. So we're going to go back to the factory thing here. Okay, so somehow this is going to go to the linear programming solver. So somehow I have to represent the input to a linear program problem. Okay? And then I have to overload the operators like and or, and greater than, and less than, things that produce Booleans to produce that representation. Okay? And then I have to somehow run this program and so on. Okay. So let's talk about abstracting Booleans. Okay? So here, there's some type B, which is bool-like. All right? And there's true, false, and or, and lift B. These are functions it has to have. There's some class num-like, okay, which implements plus and times, and it knows how to lift integers and rationals to t's. And then there's some class compare TB, a binary class, okay, which says t has to be num-like in bool, and b has to be bool-like, and then I have this compare operator. So this gives me less than, equal, and so on. All right. Okay, so the first thing you notice, if you do this linear solving, things are represented as polynomials with a constant. So a polynomial is a variable name, string, and some value n. All right, 3x plus 4y plus 7w, right? Okay, and a term, and an expression is a polynomial and a constant. So 3x plus 2y plus 7, that's the constant. Okay, and a relation, this is the thing which essentially stands for Boolean value. That's a polynomial and a range. So that says this polynomial, 3x plus 4, is bounded above and below. That's what the range is. Okay? And there are 2 relations taught in unsat that represent true and false. Okay? Then I have to do some overloading. Okay? So I have to say, well, how do I lift a constant n? Well, I make a term with no polynomial and constant n. How do I add 2 terms? Well, what do I have to add the top column? There's a bunch of clauses I haven't included here. I have to lift true to a list of relations, so that's taught. I have to do some comparisons. So anyway, I'm writing these operations, and these operations are interpreting the operations on Booleans over those abstract, those concrete representations that I'm going to throw at the solver. Okay. Then I have to do initialization. So here I had this production thing, which was an array of pairs of integers. So here you can see think of it as a table, okay? There's a row A, and then cities where the stores are New York City, Atlanta, and LA. And each of those is going to have some value. So what I've done here is I introduce a new variable, A, B, C, D, E, F, right? Okay, for every slot in that array. So initialization of arrays has to do something like that. Okay, and then I'm going to say each slot in that array gets a new variable, which is a polynomial of one, just one variable, okay, and 0 constants. So that thing now gets produced. Okay. So suppose I do something like, now I have to do a binding time analysis. Why do I have to do that? Okay, so here's one of our constraints. Okay, so for each F, which is a factory, for each F, which is a store, the production at factory F and store S, if I add all those things up, okay, then that has to be the sales for that store. Okay, so the sales, that's completely static element. I know that in advance. Okay, that, you know, the sales.s, you know, produces 3 or something like that. Okay, but the production, that's something which I don't know. Okay, so I have mixed my metaphors here. Some of the things are data that I know, and some of the things are data that I don't know. And that's exactly what you get in a kind of binding time analysis or partial evaluation. Okay, so I have to do an analysis here, and I have to say, oh, what I really need to do is compute sales.s, and then lift it into an integer. It's going to be like 7 or 12 or 22. Okay, and then I can do the rest of the. So if I use the overloaded sum and the overloaded and, I'll get some things. And so what I'm going to get here is I'm going to get some polynomials that look like this. Okay, so 1a plus 1b plus 1g is bounded below by 230 and above by 230 and so on. And I get this thing here is essentially constructed by evaluating this thing here with overloaded functions for and sum and so on. Okay? All right. Now I've got to do what? I've got to put that in the right format for a CLP solver. This is some horrible thing, you know. This thing here looks, it's done by row, but the input for the CLP solver is really done by column. So this is this horrible mess. I have all this stuff here. But you don't need to know this, right? Okay. And then when I'm all done, the output is in a file that looks like this, and it tells me the values of these things. And so those values have to be re-imported into the program. Okay? So that's I go through those 7 steps, okay? And the solver is called, it produces an output file, that output file is sucked back in, okay? The values in there are extracted and stuck into the production array, and then my program continues with whatever it is that it wanted to do. Okay? And the nice thing is that the steps here are true no matter what the solver is. Okay. So, what have we done? Okay. We've made this little fun log language, okay, which I call is a mixed modal language. That is, that it has two modes of computation. It has the evaluation modality, where you evaluate expressions to get values, and it has the find or search modality, where you essentially say there exists a variable and it has these properties, okay? And computation for the find modality is performed by some solver, okay? I tried to make this as rich a language as I could, okay? So it has integers and bools and rationals. It has sort of Pressburger arithmetic, so I could use like SMT solvers. It has tuples. It has a notion of finite sets, okay, which I use to build implementations of relations like in data. Okay. So it's flexibly scoped and so on. Okay. So what are my conclusions here? Well, it's actually good to have more than one kind of modality. Okay. You can mix your computations. The existential declaration allows you to naturally express the things that you know. Okay? There are 7 steps to embed a new solver. The first solver took me a year to implement. The fourth one took me 3 days. Okay? I got better and better for each one. Okay? These constraint types isolate the expressivity needed to state the problem. Okay, so these constraints here are exactly the constraint that you write, okay, essentially, oops, well, whatever. It goes into the constraint types. Where's slide?
Your slides are sending a message to.
Yes. Okay. The thing that took me a long time to figure out is the constraints require a binding time analysis. You can't do this as a classes in Haskell because some things are known and some things are not known. So it needs an extra step. Okay? And also that, you know, the functional abstraction is a great glue, right? We know that functional languages are good. You can tie together 2 or more of these things in a really natural way. All right.
Great, thank you very much. Perhaps time for just one quick question. So John's got one over here.